All right, howdy. So let's play with tires. I actually found a picture of a tire in case you're unfamiliar with them. What we're going to do is we're going to take this tire, and you are going to be the smart one this time. You're going to be pushing this tire on the ice, and if you're pushing the tire on the ice, it's going to move at 2 meters per second, but it's going to feel no friction, which means it's not going to spin. You might have to push it along that line so it doesn't spin, but in any event, you're on the ice and it doesn't spin. Whereas your friend over here is going to push one on the ground, so he's going to be on this footpath over here. He's going to push one on the ground, and that is going to spin. Let's put some dead grass over here, because if the lake is icy and you can see grass, it's not going to be very alive. So you and your friend are doing that. Let's fill that in a little more. So, got to fill it in because of the ice. All right, so he's going to spin that, and he's going to do some work. And we want to figure out how much work you saved yourself. So the tire, we're going to pretend has all of its mass right up there, so that it's going to be just a cylinder. We're going to pretend it's just an empty cylinder like that. Let's see, how are we going to apply this? Well, what we're going to use is the work energy theorem. So work is equal to the change in the kinetic energy. And in this case, there are two parts of the kinetic energy. There's the translational part, which is 1/2 mv squared, plus now a rotational part, which is 1/2 I omega squared. And so we're going to look at both of these. Now you only have this part because your tire here isn't rolling, it's just sliding that way. Whereas your friend is going to have both parts because it's pushing it this way, trying to keep up with you, and it's also rotating. So we just want to figure out how fast you had to accelerate the tire to get it going, and we're pretending like it doesn't slow down at all while it's going. Idealize the situation. So let's look at you. Your work, W sub u, is going to be equal to just that, 1/2 mv squared, your translational kinetic energy. Whereas your friend is going to have another part. So that's going to be equal to 1/2 times whatever that mass is, which is 10 kilograms, over here, times the square of 2 meters per second. All right, so what's going to happen there? We have 2 times 10, or 2 times 2 times 10 divided by 2, which just says 2 times 10. So we have 20 Newton meters. That's the unit for work, is Newton meters. You do 20 Newton meters of work. Now the question is how much more work or less work does your friend do? So let's look at your friend. Okay, and in this case we have your friend's work, which is equal to 1/2 mv squared, which happens to be this number, plus 1/2 I omega squared. I, we need to calculate, that is the moment of inertia, and omega is the rotational speed. But your rotational speed, because it's rolling, is going to be related to your translational speed. So rotation and translation are related because you're rolling. If you're not rolling, that's not true. So let's see how this works. So let's see, we have, or should I do this? V equals omega r. I'll do it over on this side here. Your V is 2 meters per second. Your R is 1/2 a meter per second. So if we divide 1/2 by both sides, or if we multiply both sides by 2, we end up with omega is equal to 1/2 meters, 4 inverse seconds, or 4 hertz. We'll just use inverse seconds, radians per second. So we've got that part. We need to find I. I for a cylinder with all of its mass right at the edge, which is what we're going to pretend to do. For the 206 class, for the calculus-based class, I actually give them a problem where they get to work out the exact moment of inertia of a tire, and they hate me for it. That's going to be just mr squared for our approximation, and somewhat less for our perfect description. Mr squared is your mass, which is 10 kilograms. Your radius is 1/2 a kilogram squared, so that's going to be equal to 2.5 kilograms, or 1/2 a meter squared. All right, so the work your friend does is equal to 1/2 times your mass times your velocity. Like I just said, that's just 20 Newton meters. We just did that, so we don't have to do it again. Times, or plus 1/2 I, which is this guy, 2.5 kilograms meters squared, times this guy over here squared, 4 inverse seconds, which is 16 inverse seconds squared. I didn't mean to do that. I just did it in my head by accident. Sorry. So all we have to do is multiply all this stuff together. So we have 20 Newton meters plus 1/2 divided by 16, or 1/2 times 16 is 8. Now we take 4 of those and that gets us to 10, and then we take the other 2 and that gives us 20 Newton meters. And so we have the happy accident that both the rotational and the translational energy that your friend has to impart are the same number. It doesn't have to be that way, but it can be that way, and it happens to be that way here. So we have 40 Newton meters. Okay, so that was an application of the work kinetic energy theorem for rotational motion. It still works the exact same way. You have work is equal to stuff plus stuff, just all your different kinetic energies. So the amount, if you're the only thing that's putting energy into the system, if you're the only thing that's doing work to it, or I guess your friend is the only thing that's doing work for it, then every degree of freedom, velocity, rotations, whatever, they all have to come from that same work that you're doing. So that's you plus, or the amount of work you did plus however extra it is. So that turned out to be that you did 20 newtons per meter less work by letting it slide. So if you can let something really truly slide, it's better. Now, what happens normally? Well, normally, when you have something rolling, it's easier, and that's because it's easier to keep the thing going, not necessarily to get it started, right? So it's easier to get the stationary thing, or the non-rotating thing started. But if you have some other effect, let's say friction, which is the thing that's causing the rolling, well, that friction in one case is causing your wheel to roll, and it's actually helping you out, whereas the other case, what it's doing is it's slowing you down. But in this particular case, you win by 20 Newton meters, all right? So I hope you feel like a winner. I hope you're having a great time. I will talk to you in just a moment. Bye now.